Welcome to the deep dive. We get straight into it, giving you the core knowledge you need efficiently.
Yep, no messing around. You're here to learn, so are we.
And today we're diving into renewable energy, specifically biomass.
That's right, and we're really digging into one specific source today. YouTube Lecture 6 from Professor Supriya Ghosh.
Ah, yes, from his 2021 Renewable Energy Resources course at ICT Mumbai. That's GTT 2105 for anyone keeping score.
Exactly, Institute of Chemical Technology, Mumbai, and we've got the link for you in the show notes. It's right there on YouTube.
Good stuff. And it's worth saying, this is just one lecture, Lecture 6 out of 15 he delivered, so there's a lot more context there.
Definitely. And actually, Lecture 5 is pretty useful background, too, also on his channel. We'll link that as well.
So think of this deep dive as, well, our way of pulling out the key bits from Lecture 6 for you.
Our mission, basically, is to unpack the core ideas about biomass energy from this lecture, make it clear, engaging.
And hopefully make you curious enough to go watch the full thing yourself.
Precisely, maybe even the whole series.
Okay, let's get started. Professor Ghosh kicks off with this idea of upstream and downstream for biomass energy. What's that about?
Right. So upstream,
Yeah.
that's basically the biomass itself, the raw material, where
Yeah.
it comes from.
Like forests, farms, that
Mhm.
kind of thing.
Exactly. And he points out a really critical upstream issue right away,
Mhm.
this potential clash between using land for food versus using it for fuel crops.
Ah, the food versus fuel debate.
Yeah,
That's a big one.
it really is how we use our land,
Yeah.
So that's upstream.
So downstream must be what we do with the biomass.
Pretty much. Downstream covers all the conversion processes,
Mhm.
turning that raw stuff into actual fuels.
Okay.
And Professor Ghosh says, look, theoretically, you could turn biomass into almost anything,
Yeah.
but there's always a penalty.
A penalty, like
Yeah.
drawbacks.
Yeah, two main things. First, carbon conversion efficiency. How much of the carbon in the original plant actually ends up in your final fuel? You lose some.
Right, lost as CO2 or used up in the process itself.
Exactly. And second, the chemical intensity. How many sort of harsh chemicals do you need? That affects the environment, the cost.
Gotcha. So minimizing that penalty is key. Okay. He then breaks biomass down into three categories. Primary, secondary, tertiary. Can you walk us through those with his examples?
Sure. So primary biomass,
Yeah.
that's the direct result of photosynthesis, stuff grown directly.
Like trees.
Woody crops,
Yeah.
yep, or seeds from oil crops, and also agricultural residues, the stalks and leaves left over after you harvest the grain. That's all primary.
Straight from the field, basically.
Right.
What about secondary?
Secondary biomass is what you get when you process that primary stuff. It's the byproducts.
Sawdust.
Sawdust from milling wood, exactly.
Hmm.
Or bagasse, that fibrous stuff left after crushing sugarcane. He also mentions black liquor from paper mills, animal manure, distillery waste.
Okay. Leftovers from processing.
Right. Although he does say the line between agricultural residues like straw and secondary biomass can sometimes be a bit fuzzy.
Okay.
It's a good point.
Okay. And the last one, tertiary.
Tertiary biomass is stuff that's already been used for its main purpose and is now waste.
Like old cooking oil.
Yeah, rancid vegetable oil
Mm.
or used cardboard boxes, paper packaging, even wood debris from demolished buildings. It's the end-of-life biomass.
Primary, secondary, tertiary. Got it. Clear categories. So the lecture then shifts to the biomass to bioproducts interface, focusing on energy.
Yeah, moving from the raw material to something useful. Now, biomass can be used for lots of things, pharmaceuticals, high-value chemicals.
But the focus here is energy.
Right. For Lecture 6 and for us today, it's mainly about biofuels and power generation. Energy is the key target.
Okay. So how do we get that energy? What are the main conversion routes?
Professor Ghosh lays out two main pathways: biochemical and thermochemical transformations.
Using biology or using heat, essentially.
Pretty much. And for this lecture, the deep dive is really into the thermochemical side, using heat to transform the biomass.
All right. So what kind of thermochemical methods does he cover?
Well, he lists several. Some, like anaerobic digestion or fermentation, which are actually biochemical but sometimes discussed alongside, might need some pre-processing first.
Pre-processing, like breaking the biomass down.
Yeah, maybe chemical treatments or physical methods like steam explosion, just to make it easier to convert.
And then after the main conversion,
Often you need post-processing too. Concentrated the product, purifying it.
okay. What are the main thermochemical processes he focuses on?
He mentions pyrolysis, gasification, and depolymerization that's breaking down the big molecules. He also briefly touches on chemical stuff like lignin chemistry, turning lignin into things like lignosulfonates, which are surfactants.
Wow, lots of options. But the end goal is
Biofuel and energy, that's the main drive here.
And he mentioned something about research publications skyrocketing.
Yeah, it's quite striking. Since around 2000, the number of papers on bioresources and bioenergy has just exploded. Exponential growth.
Suggests a lot of activity, a lot of potential maybe.
Huge potential, huge dynamism in the field. But, and this is a key point he makes, research isn't enough.
Right. It has to actually work in the real world.
Exactly. Turning research into viable tech needs constant improvement, and it has to be demonstrably useful. Better than what we've already got, ideally.
Makes total sense. Okay, a really fundamental concept here is calorific value. Why is that so important for biomass?
Calorific value is just the energy content, right? How much heat you get when you burn it. And it's crucial because, well, generally you want to start with biomass that packs more punch. More energy content makes the whole process more efficient.
And he links this to the chemistry, the oxygen to carbon and hydrogen to carbon ratios. How does that work?
Yeah, it's interesting. Lower oxygen to carbon ratio usually means higher heating value.
Why is that?
His analogy is good. If there's already a lot of oxygen in the fuel molecule, it's like it's already partially burned, so there's less energy left to release when you fully combust it.
Ah, I see. So less oxygen is better, energy-wise. What about hydrogen?
Higher hydrogen to carbon ratio also generally means higher heating value. Think methane, CH4, versus pure carbon, C.
Methane burns hotter.
Well, the carbon's in a lower oxidation state, so it releases more energy going to CO2. Plus, the hydrogen burns to water, releasing energy too.
So ideally, low oxygen, high hydrogen for the best biomass fuel.
That's the general idea. He uses a conceptual plot in the lecture to show where things like coal, lignite, wood, and cellulose sit based on these ratios.
Where does wood fit in? And cellulose?
Wood and cellulose are higher up in oxygen compared to coal. Interestingly, pure cellulose has a higher OC ratio than wood itself.
Really? Why?
Because wood also contains lignin, and lignin has relatively more carbon and hydrogen and less oxygen compared to cellulose.
Fascinating detail. And he also connects this back to coal's origins, doesn't he?
Yes, reminding us that coal is fossilized biomass. It started as plants, then over millions of years lost oxygen and hydrogen, becoming concentrated carbon. It's a continuum.
Right. Okay, how do we measure this calorific value? What units?
Two main systems. English units are BTU per pound British thermal units. Metric uses kilojoules or megajoules per kilogram.
And what exactly is a BTU?
It's the energy needed to heat 1 pound of water by 1 degree Fahrenheit. He gives a conversion too. 1 BTU is about 1.055 kilojoules. And BTU pound to kJkg is roughly a factor of 2.2.
Got it. Now he makes a distinction between higher and lower heating value. HHV and LHV, what's the difference?
Super important distinction. Higher heating value, or HHV, includes all the heat released, even the latent heat recovered when the water vapor produced during combustion condenses back to liquid.
So capturing everything, and LHV.
Lower heating value, LHV, doesn't include that heat from water condensation. It assumes the water escapes as vapor, taking that energy with it. It's the net value.
So for something like pure carbon, anthracite coal, would HHV and LHV be different?
He clarifies they'd be the same, or very nearly the same, because burning pure carbon doesn't produce water. The difference only matters for fuels containing hydrogen.
And he gave that practical example, tool industries, recovering heat.
Yeah, great example. They cooled the flue gas from their natural gas boilers. The water vapor condensed, and they recovered that latent heat in the water itself. Saved energy, saved water.
Right.
Shows why understanding HHV versus LHV matters in the real world.
Absolutely. Okay, let's talk about agricultural residues specifically. What's the general picture for their calorific values?
Generally, most agricultural residues are quite similar because they're mainly cellulose. Their heating values are in the same ballpark.
But some variation exists.
Oh yeah. Things with more CH bonds, like lignin-rich parts, will have slightly higher values. On the other hand, things like municipal solid waste, MSW, or refuse-derived fuel, RDF, often have lower values.
Why lower?
Usually higher moisture content and just a more mixed, less energy-dense composition. Interestingly, newspaper, being mostly cellulose, has values pretty similar to agricultural residues.
And he mentioned switchgrass.
Yeah, fast-growing grasses like switchgrass have similar energy potential to things like sugarcane bagasse, again because they're largely cellulosic.
So the takeaway is, it depends on what's around.
Exactly. Local availability is often the deciding factor for what biomass you actually process.
Makes sense. Right, let's dig into those thermochemical processes now. Combustion first.
Combustion is the most basic, right? Reacting biomass with plenty of air or oxygen to burn it completely produces CO2 and hot gases.
And those hot gases?
You can use them directly for heat in industrial processes or use them to spin a turbine and generate electricity. Pretty standard stuff.
Okay. Next step, gasification. How's that different?
Gasification is like controlled combustion. You deliberately limit the oxygen.
Why limit the oxygen?
So instead of complete burning to CO2, you get partial oxidation, producing producer gas, or syngas, that's mainly hydrogen, H2, and carbon monoxide, CO.
And what can you do with syngas?
It's combustible itself. You can burn it for heat, or, as he mentions, use it to run internal combustion engines for power.
Interesting. Okay, then pyrolysis, what happens there?
Pyrolysis is heating without oxygen, or very, very little, anaerobic heating that decomposes the biomass.
What do you get out of pyrolysis?
Depends on the conditions, but key products he highlights are methane gas, CH4, and char, which is basically charcoal.
So you can get gas or solid fuel from pyrolysis. And the last one, liquefaction.
Yeah, the goal there is liquid fuels, converting solid biomass into liquids, usually needing hydrogen and high pressure. Hydrothermal liquefaction, HTL, is a key method.
Aiming for transport fuels, presumably.
Exactly, given how much liquid fuel we use for transport.
Okay, so combustion heat, gasification, syngas, pyrolysis, char, liquefaction, liquids. Got the basics. Now, Professor Ghosh talks practicalities, handling biomass.
Yeah, it's not trivial. Raw agricultural residues like straw or stalks have really low bulk density. They're fluffy, take up loads of space.
Making transport a pain.
Totally inefficient. So he emphasizes densification technologies, things like baling machines or machines that make briquettes or pellets.
Compacting it down.
Right. Makes it much easier and cheaper to transport and better suited for feeding into power plants or reactors. He shows some examples in the lecture.
Good point. Another practical issue.
Yep. All biomass has some inorganic stuff in it. When you burn it, that's left behind as ash.
Is all ash the same?
No. The composition varies a lot depending on the plant, the soil it grew in.
Yeah.
Sometimes it even has useful nutrients you could potentially return to the soil.
But it can cause problems too.
Oh, big time. The main problem is ash melting at high combustion temperatures. It forms clinkers, sticky, hard deposits.
And that's bad because
It can clog up the equipment, block airflow, coat heat transfer surfaces. Basically, it messes up the whole combustion process and reduces efficiency. He shows a cone test illustrating how ash deforms and melts as temperature rises.
what makes it melt? What's in the ash?
Mostly alkali metals like sodium and potassium, alkaline earth metals like calcium and magnesium, and silicon dioxide.
And some biomass types are worse than others.
Definitely. He compares typical wood ash with rice straw ash. Rice straw has a lot more silica.
High silica, like sand.
Pretty much. He says its composition is similar to borosilicate glass. So at high temps, rice straw ash readily melts into a glassy slag. Huge problem for boilers.
Wow. Any way around that?
He mentions possibly leaching out some soluble bits from the rice straw beforehand to change its melting behavior. But it's a real challenge.
But there was a potential upside to that silica.
Yeah, the glass angle. Because it's so silica-rich, people have actually looked into using rice straw ash as a raw material for making glass. He cites a paper on it, turning a problem into a product.
Resourceful.
Yeah.
Okay, he then introduces isopliths. What are those about?
Isopliths in this context are lines on a chart connecting different biomass types that have the same concentration of a specific component, say potassium oxide, K2O, within their ash, even if their total ash amount differs.
So it helps you find biomass with specific ash characteristics.
Exactly. If you want high potassium ash for fertilizer, or maybe low alkali ash to avoid clinkering, isopliths can help you map out which biomass sources fit the bill based on their typical ash composition and content.
Clever tool.
Yep.
Okay, back to combustion. Low-tech versus high-tech examples.
Low-tech, he gives the example of a simple stove, a chula. Temperatures are lower, so ash melting is less of an issue there.
And high-tech.
A more sophisticated direct combustion system. It has controlled primary air for the main burning and secondary air introduced higher up.
What's the secondary air for?
To burn off any uncombusted gases or soot coming off the primary zone. Leads to more complete combustion, higher efficiency, less smoke.
Makes sense. He also mentioned toxic byproducts like dioxins.
Yeah, a critical issue. Dioxins can form during combustion, especially under certain conditions. He emphasizes it's temperature dependent, surprisingly. Too low a temperature can sometimes be worse for dioxin formation. So you need optimized conditions.
Tricky balance. Okay, a more advanced combustion method. Fluidized bed combustors. How do they work?
They're pretty neat. You have a bed of sand-like material. You blow air up through it fast enough that the particles start moving around, acting like a fluid. Then you mix finely ground biomass into this fluidized bed.
What's the advantage of that?
You get incredibly good mixing between the fuel particles and the air. Leads to very efficient, complete combustion. Plus, the heat transfer is excellent.
Any benefits for emissions?
Yes. Because the temperature can be controlled more uniformly and kept below, say, 950 degrees C, you can minimize the formation of NOx. And as he notes referencing an EPA study, they produce significantly fewer dioxins compared to older incinerator types, especially for things like MSW.
Sounds great. Downsides.
Higher capital costs, usually.
Yeah.
And you need energy to grind the biomass into fine particles, unless your feedstock is already fine, like sawdust. That works well directly.
Okay, shifting gears to gasification again. Let's get more detail. He described a downdraft gasifier.
Right. Downdraft means the fuel goes down, and the product gas also goes down. Fuel fed at the top, air usually comes in from the side, partway down.
And different zones form inside.
Yeah. Where the air enters, you get oxidation, basically combustion providing heat. Above that, the heat dries the incoming fuel and causes pyrolysis, breaking it down without oxygen.
What are the key chemical reactions happening?
Several important ones. Carbon reacting with CO2 to make more CO. Carbon reacting with steam, water, to make CO and hydrogen, the water-gas reaction. Then there's the water-gas shift reaction, balancing CO, water, CO2, and hydrogen. And some methane can form too.
So the producer gas is a mix of CO, H2, some CO2, methane, water vapor.
Exactly. Primarily CO and H2, the syngas. He also briefly mentions updraft gasifiers, air in at the bottom, gas out the top. They handle wetter fuel, more ash, but make more tar.
Tar is bad.
Yeah, tar's and messy stuff. Sticky, clogs things up, needs removal. Fluidized beds can also be used for gasification, by the way.
And he showed an actual gasifier unit.
Yes, a real-world example producing producer gas that could then be burned directly or fed into an engine to generate power.
But you need to clean the gas first.
Usually, yes.
Yeah.
Tar removal, getting rid of particulates like ash and soot and drying it. Essential steps before using it in an engine, for instance.
How efficient is gasification?
He defines efficiency based on the energy in the producer gas compared to the energy in the original biomass. Then, if you generate electricity from that gas, the engine efficiency is maybe 30–40%, so the overall biomass to electricity efficiency is lower.
Okay, so we have this producer gas, the syngas. What else can we do with it? This seems like a key area.
Absolutely. He shows how they monitor the gas composition using gas chromatography, tracking CO, methane, hydrogen over time. Gives an example of about 65% gasification efficiency and maybe 24–25% overall power efficiency.
But the really exciting part is using syngas chemically.
Yes, Fischer-Tropsch synthesis. It's a process that takes syngas, CO and H2, and converts it into liquid hydrocarbons. Basically, synthetic diesel or petrol.
From biomass.
From biomass, via gasification first. He mentions a company, BTL Biomass to liquid, making sun diesel this way.
Wow. What kind of scale?
Pretty significant. Processing maybe 200,000 tons of biomass a year, but needing 1 million tons of feedstock. Shows the logistics involved.
And the carbon efficiency. How much biomass carbon ends up as fuel?
About 42%, according to his figures. The rest is lost, mostly as CO2 during the gasification step itself. So still challenges there.
Huge potential, but challenges remain. Okay, let's look at pyrolysis again, focusing on charcoal.
Right. Pyrolysis is anaerobic heating. It dries off volatile stuff and leaves char, which is mostly carbon. He explains that for things like cellulose, it's essentially removing water, concentrating the carbon, without changing its oxidation state much.
How efficient is making charcoal? Wood to charcoal ratio.
Traditional kilns, he says, maybe 4.5 tons of wood make 1 ton of charcoal. Modern ones are better, maybe 3.6 tons of wood per ton of charcoal.
And he gave that amazing example from Brazil.
Yeah, the Brazilian steel industry. Since the 1920s, they've used massive amounts of charcoal made from eucalyptus forests as a reducing agent instead of coke from coal.
Really? How much?
Millions of tons of pig iron produced using this charcoal. In 2002, it was 7.8 million tons, probably more now. It involves huge areas of managed eucalyptus plantations.
Sustainable forestry for steelmaking.
That's the aim, cutting and replanting. He notes it involves hundreds of thousands of people. But he also cautions that Brazil has land availability that places like India don't, making direct replication difficult.
But charcoal is made elsewhere too on a smaller scale.
Oh yes. In India, using things like leaf litter, sugarcane trash, rice straw, he describes a simple low-tech method. 2 drums, one inside the other. Burn stuff in the outer drum to heat the inner one anaerobically.
And make charcoal inside.
Exactly. Takes a long time, maybe 30 days, but it works.
What's the charcoal like?
Pretty good. Low moisture, around 7%. High fixed carbon, over 80%. Low ash, low sulfur, high heating value. Makes decent briquettes.
So what are the advantages of charcoal over just using the raw biomass?
Higher energy density because it's concentrated carbon, burns cleaner, less smoke, easier to transport and store. And as Brazil shows, it could potentially replace coke in some industrial uses.
Makes sense. Okay, another liquid fuel route, hydrothermal liquefaction, HTL.
Right, another thermochemical path to liquids. Important for transport fuels. Key things. Needs hydrogen, high pressure like 3000 psi, 220 bar and moderate temperature, around 350 degrees C.
High pressure sounds like a challenge.
Big challenge. Reactor design, cost of running it continuously. These are hurdles,
Yeah.
but a huge advantage. HTL can handle wet biomass.
Ah, no need for drying.
Exactly. That saves a lot of energy compared to processes needing dry feedstock.
How does HTL work, roughly?
You put wet biomass under that heat and pressure with water. It converts into a liquid called biocrude and an aqueous phase with dissolved organics. That water part might be usable for biogas later.
And the biocrude, is that usable fuel?
Not directly. It needs upgrading, usually catalytic hydrotreatment, reacting it with hydrogen over catalysts at high temperature to remove oxygen and refine it into hydrocarbons.
Then you can fractionate it.
Yeah, distill it like regular crude oil to get gasoline, diesel fractions, etc.
And the high pressure temperature conditions relate to water's properties.
Yes, near its critical point, water acts differently. It becomes more self-ionizing, acting as both an acid and a base catalyst, helping break down the biomass, using the reaction medium itself.
Clever chemistry. He gives an example using jatropha for jet fuel.
Yeah, building on earlier work with jatropha for biodiesel. Regular biodiesel can freeze at altitude, which is bad for planes.
Right. Very cold up there.
But this HTL process, followed by hydrotreatment, produces highly branched hydrocarbons from jatropha oil.
And branching helps with freezing.
Exactly. Branched molecules have much lower freezing points, making them suitable for blending into jet fuel. He mentions a Boeing 747 flue using a blend made this way.
Impressive. What are the overall considerations for HTL?
Feedstock matters. Cellulosic stuff needs more hydrogen input than, say, vegetable oils. And you always have to ask about the overall energy balance and sustainability, especially if you start with refined oils.
But the pros are?
High carbon efficiency, works with diverse feedstocks, conceptually simple, and that big plus of handling wet feeds.
Current status. Commercially ready.
Not yet deployed commercially, he concludes. Still working on the high-pressure pumps, reactor designs, and bringing down the capital costs. Lots of potential, but still under development.
Okay, one last major area. Biomass to biogas via anaerobic digestion.
Yes, a biological route. Fermentation by microbes without oxygen. He calls it a more intelligent way to handle wet biomass compared to something like HTL.
Common in India.
Particularly for treating waste streams like spent wash from ethanol plants. The main product is biogas, which is mostly methane, CH4.
Advantages of biogas production.
Handles wet biomass well. And methane isn't very soluble in water, so it naturally separates out as a gas, simpler downstream processing compared to getting liquids out of water.
How is it typically done?
He describes large-scale digesters, sometimes like flexible pillow tanks or balloons. You feed in biomass slurry with microbes, let it digest anaerobically for weeks, and collect the gas.
Any useful byproducts?
Yes, the leftover digested sludge is a great fertilizer, closes the loop.
Does the biogas need cleaning?
Often, yes. It contains hydrogen sulfide, H2S, from sulfur in the biomass, which is corrosive and smelly, and a carbon dioxide, CO2, from the process. These usually need removing, maybe with alkali scrubbing for CO2.
And he finished with that point about cows and methane.
Yeah, and an interesting side note, ruminants produce a lot of methane. Since methane is a potent greenhouse gas, there's research into reducing those emissions. Maybe through diet changes, he mentions seaweed additives being studied in India.
Connects biogas as a fuel source to methane as an emission concern.
Exactly. Shows the complexity. Methane is both useful and problematic.
It really covers a huge amount, this lecture. So many pathways and factors to consider.
Absolutely.
Yeah.
Professor Ghosh's lecture goes into way more detail, of course. We've just tried to hit the main points from Lecture 6 today.
Hopefully we've given everyone a good overview and maybe sparked some interest to check out the original source. That link is in the notes.
Definitely worth a watch if this topic interests you. Which brings us to a final thought, something to chew on.
Okay, let's hear it.
Thinking about your own local area. What overlooked biomass sources might be lying around? Things people aren't really using for energy yet.
Interesting. Like specific local wastes or plants.
Could be. And then, based on what we've discussed today, combustion, gasification, pyrolysis, HTL, biogas, Which conversion method might actually make the most sense for that specific resource, considering efficiency, practicality, and environmental impact?
That's a great question. Forces you to apply these concepts to a real-world scenario.
Exactly.
Well, we hope this deep dive has been useful and got you thinking about the fascinating, complex world of biomass energy. Keep exploring.